Hi everyone, Mr. Boltri here bringing you video 3.4. We're going to talk about the physics concept of work. To do so, we are going to give a definition of work and then give several different ways to calculate work. So first, what is work? Well, like the Rihanna song by the same name, a lot of people have trouble understanding the physics concept of work because it's different than our intuitive natural concept of work. Because in physics, work has a very specific definition, and that is the energy that is put into or taken out of a system. We call that work. And we've seen this before. We've talked about conservation of energy. Now, up until this point, mostly work has been zero because that allows our system to be closed and the final energy to equal the initial energy. But if energy is put into or taken out of the system, that's going to be positive or negative work, respectively. So you can see work, which is represented by a W, in all of these equations below. And probably the easiest one to remember is the change in energy equals work. So that's one way that we can try to figure out how much work was done on an object, is to see how much the energy changed. So for example, just as a basic definition, we can say that work is a measurement of the amount of energy transferred to or taken from an object. And this occurs mostly when a force is applied to an object, moving it through some displacement. So you can imagine if I applied a force to a book that was sitting on a table and the book didn't move, well then no work occurred, which this is how it's different from the colloquial definition of work, is that if I was pushing down on the table and I did that for an hour, you might say that I was doing work. But if it doesn't move at all, then no work was done. So that's a really important distinction that we need to draw. So we can use that definition to actually calculate the amount of work. So for example, if I pick up my cat from the floor and move her to the couch, how much work did I do? So we can see her gravitational potential energy. If we take the floor as the reference point, then her initial gravitational potential energy is zero. If she's not moving, she has no kinetic energy and there's no springs involved. So then when I lift her up and move her from the floor to the couch, then I do change her gravitational potential energy from 0 joules to 20 joules. So therefore, I must have done 20 joules of work to get her from the floor to the couch. So that's one easy way to figure out how much work was done, just by seeing the initial energy and the final energy. But you're not often going to be given a situation that's this clean and simple. So I'm going to give you some other ways to calculate work as well. So more often, you're going to be given something like this. If I apply, so now I'm not raising a cat, I'm raising a physics textbook and applying a force that's shown over here. We're going to say this force is in the upward direction. So if I apply 20 newtons of force and I raise it 0.8 meters, which is like the distance from the floor to the tabletop, how much work did I do? Well, we could try to figure out how much the gravitational potential energy changed, but it's going to be hard to do that without knowing the mass of the book. So we're going to have to take this from a different approach, and we're going to have to think back to the times when we derived energy from the graph. Now we remember a joule is a Newton times a meter. So it stands to say, well, if I take the force, newtons, and multiply it by the meters, then I am just basically integrating this graph, and that might give me the work. And if that is your guess, then you'd be correct. So 20 times 0.8 is going to give the work by Mr. Boltri. So another way that we can think about work is just the integral of the force displacement graph, where R in this situation is the displacement. So in this situation, it would be 16 Newton meters, which is just the same as 16 joules for the amount of work. So that's another way that we can think about trying to approach work. But the thing that was probably a little bit oversimplified about this example is that I was just sort of raising the book up. So the force that I was applying was in the same direction as the displacement. But what do we do if the force is in a different direction from the displacement? For example, we've seen this example before with Mary pulling a sled along the ice. So it is speeding up, so we can tell that there is some work being added to the system because it's changing its kinetic energy. But we're not given really any information about its mass or any information about its velocity before or after she's pulling on it. So we're going to have to use the force through a distance approach to calculating work. However, if we look at her force of 30 newtons, hopefully remembering from the force unit that some of that 30 newtons is to the right, but also some of that 30 newtons is up. So the 30 newtons in the up direction is just causing force normal. It's causing the ground not really to have to push as hard. So the vertical component of this force tension is not contributing to the sled speeding up, only the horizontal component of the force tension. So if we integrated 30 newtons through the displacement of 15 meters, we would get an overestimation of the work because not all 30 newtons are causing the sled to speed up. Instead, what we need to do is we need to figure out the horizontal component because that's in the same direction as the displacement, and then integrate the 26 newtons through those 15 meters. So it's not the force through the distance that is being applied, it's the force that it also happens to be in that same direction as the distance. So in this situation, since the displacement was in the horizontal direction, we're going to look at the horizontal force and do the horizontal force times the displacement. So another way you can think about that is if you're given an angle between the force and the displacement, then we can find the work by doing the force times the cosine of that angle through the displacement. So this is kind of a more advanced formula. This formula is going to work in more circumstances. The force doesn't have to be in the same direction as the angle. You'll notice this is the same formula as the one that we had before, but the cosine of 0 is 1. So it's just going to be the force through the displacement if they are in the same direction. Another way to think about using this equation is what about work in uniform circular motion? So if the object is spinning in a horizontal circle, maintaining a constant velocity, its gravitational potential energy is not changing, and its kinetic energy is not changing because kinetic energy uses only the speed, doesn't really care about the direction. So how does this also work with our formula? Well, remember the force is towards the center of the circle and the direction of the displacement at any instant is perpendicular to the circle. So the angle between them is going to be 90 degrees. So the force times 90 degrees, if we integrate that through the distance that it's traveling, is going to be 0 joules. So that makes sense because it matches our formula and it matches the conservation of energy principle. But last but not least, so AP is not always so nice as to give you the angle between two things that are going on. So they might just give you two vectors that would look like this. A force, which is 3 in the horizontal direction and 4 in the vertical direction, moves an object through a displacement of 10 in the horizontal direction. So how much work was done? So whenever you have a situation like this, the first thing you're going to want to do is draw a diagram. So we'll notice that this example is a lot like the example that we just did, in that we're only going to take the horizontal component of this force, the 3 newtons, and multiply it through those 10 meters. So the answer at the end of this problem should probably be 30 joules, but we're not always going to be given something that's very nicely horizontal like this. This displacement vector might also be at an angle, and then it would be a little bit trickier to do. So we might want to try to use our F cosine theta through the displacement formula, but and which we could do, we could find the angle there, but in this situation, I'm giving you an overly simplified situation so you can see the techniques to use in a more complicated situation. Though I just want you to know it would work to find the angle, do F cosine theta, and then multiply it by the displacement. Or we could just say, okay, well, since this is entirely to the right, we're just going to take the rightward component of the force. But let's look at another way to do it. I'm going to introduce you to a new concept. And this is going to be less, it's not going to work as often because we're not given the theta. So it's not going to be worth our time to calculate the theta when there's a much easier way to do it, which I will show you now. And it's something called the dot product. And the dot product, which is also called the scalar product, is a way to take two vectors and basically figure out how much of vector A is in the direction of vector B. And then we can do our integration over the distance. So the way that you would do this, it's the dot product or the scalar product is the projection of A onto B. So the way that you do it is you take the horizontal components. Let's say this A looks to be 2 to the right and then 3 up, and the B is 5 to the right and then 1 up. So we're going to take the two parts that are to the right and multiply them by each other. A in the I direction and B in the I direction. Then the two parts that are in the vertical direction and multiply them by each other. And then we're going to add those two together. So in this situation, it's going to be 2 times 5, because those are both of the horizontal components, plus 3 times 1. And that's going to give us A dot B is 13, which again is the projection of A onto B. So let's see what this looks like in our work situation. So we're going to do the horizontal components and the vertical components scalar multiplied or dot product together. There's going to be 3 times 10 plus 0 times 4 is going to be 30 joules. So this actually is the same as what we had predicted it to be, because it's really only looking at the horizontal component multiplied through that horizontal displacement. So this is going to be an easier way to find work if you're given the vectors of the force and the displacement vectors. So looking at our final formula, if we do the dot product between force and the displacement, and that's what this little dot means, it's a dot product or the scalar product, which I just showed you, then that is going to give us the work if we're given a vector for force and displacement. So each of these equations is useful in different situations. If we can figure out the change in energy, we're going to want to calculate work that way. If the force is in the same direction as the displacement, then it's really easy. And this is kind of the simplest way. If we're given the angle, then we can use this formula. And if we're given vectors, then we can use this formula. And I just want you to understand that these formulas are all saying the exact same thing, especially these three. It just depends on how complicated the problem is. It depends on how complicated of an approach that we're going to need to take. So this is Mr. Boltri for now, wrapping up video 3.4. We're going to do a lot of practice with this new concept of work in our next class. So I'm looking forward to solving those problems with you then. And for now, go Bears.